Okay, so we have problem number 9 here about the space probe and Lagrange multipliers and all this stuff. What things boil down to is that we want to minimize or maximize t of x, y, z is 4 times y, z, subject to the constraint x squared plus 4y squared plus 4z squared is equal to, that's a 16. Let me write that a little bit neater there. Okay, so Lagrange multipliers, the gradient of, oh, we're using t, not f here, gradient of t is equal to lambda times the gradient of g. Okay, so this would be, the gradient of t is going to be the x partial derivative here is 0. The y partial derivative is 4z. The z partial derivative here is 4y. Is equal to lambda times 2x, 8y, and 8z. So the system of equations we have is 0 is equal to lambda times 2x. Then 4z is equal to lambda times 8y. And 4y is equal to lambda times 8z. And then, of course, the constraint 4x squared plus, x squared plus 4y squared plus 4z squared is equal to 16. Okay, so we need to solve these equations here. I'm going to kind of do it by cases. So this first one, let's see, there are 2 possibilities here. There is 0 is equal to lambda times 2x. We have 2 possibilities. So this says either lambda has to equal 0 or x has to equal 0. I'm going to take the easier case first. I'm going to take the case where lambda is equal to 0 first. If lambda is equal to 0, then the second equation becomes 4z is equal to 0 times 8y. That's just 4z is equal to 0. 4y is equal to lambda times, is equal to 0 times 8z. 4y is equal to 0. And so the consequences here is that z is equal to 0 and y is equal to 0. We substitute in that into this equation down here. X squared plus 4 times 0 plus 4 times 0 is equal to 16. We see that x can be either plus 4 or negative 4. And in this case, y and z are both 0. So we have found 2 critical points so far. Okay, so everything in this low bottom right corner is assuming lambda is equal to 0, and these are all the consequences. Now let's do the case where x is equal to 0. Okay, so if x is equal to 0, we don't get things as instantly as we did before. Now we just have our remaining equation. So 4z is equal to lambda times 8y. 4y is equal to lambda times 8z. And now this equation down here, we're assuming x is equal to 0. 4y squared plus 4z squared is equal to 16. Okay, so dealing with this, I'm going to multiply, let's make the right sides equal to each other. I'm going to multiply the first equation by z. I'm going to multiply the second equation by y to get this first equation becomes 4z squared is equal to lambda times 8yz. Then 4y squared is equal to lambda times 8yz. The right sides are equal, so we see that 4z squared must equal 4y squared, which of course is just z squared is equal to y squared. So z squared is equal to y squared. We can replace this z squared with y squared. 4y squared plus 4 times y squared is equal to 16 here. And let's see if we divide everything here by 4. If we divide everything here by 4, we end up with 2y squared is equal to 4, or y squared is equal to 2. And so y is either equal to plus or minus square root 2. Okay, so if y is equal to plus or minus square root 2, z is equal to this squared, and so z is also equal to, z squared is equal to 2, so z is also equal to plus or minus square root 2. And we end up with 4 critical points. What are the 4 critical points here? So x has to equal 0. Y can be square root 2 or negative square root 2. And z can be square root 2 or negative square root 2. Okay, so we have these 4 points here, along with these 2 from before. And so what is going on here? We just have to evaluate the temperatures for YZ at these 6 points. And so if we do that, the temperature of X, Y, Z, 4 times this, okay, so that would be 4 times 2 is 8, this would be negative 8, this would be negative 8, this would be 8, and then the temperature here would be 0 in each case. So these points give you the hottest temperature, these points give you the coldest temperature, these ones are in between. And then if you're asked for the Lagrange multiplier, just go back and reverse engineer, plug in these values for y and z into this equation to solve for lambda.